So in this project, we're going to focus on a single unified goal, which is separating vocals and instruments from a mixed music track using a UNet-based deep learning model. This is a meaningful real world challenge because sometimes music producers, DJs, or other artists need clean vocal stems or instrumental only versions to create new music. And traditionally, isolating vocals requires manual filtering, which is time consuming and inaccurate. So, our model automates this process and produces a clean stem that can be used for sampling. So, everything in this project is built towards solving this one specific problem. So, a system overview, our approach is to train a unit model to operate on spectrograms, learning masks that isolate vocals and instrumentals. So our pipeline consists of data processing.py, which converts raw audio into spectrograms and ratio masks. Then dataset.py, which organizes the database stems and prepares the model-ready tensors. Unit.py defines the unit that predicts the separation masks. And train unit, like a training loop for unit, contains the optimizer, scheduler, and checkpoints. And scoring.py, which computes evaluation metrics, MSAE, MAE, MEL1, SI. And then all these components work together. The preprocessing feeds into the dataset loading, the dataset feeds into the unit, and the unit output masks sort of feed into the scoring, which evaluates the separation quality. We did have to make our own database. So we were using the Muse DB18 database, but the issue with this database is that it splits a song into the bass, the drums, the mixture, other, and then vocals. But what we're interested in is the vocals and sort of the instrumental. So we needed to figure out a way to make an instrumental. So then we wrote this script, merge tracks, which will merge the bass, the drums, and other into a mixture.wav file. So then our resulting database ended up looking like this. In addition to using the Muse DB18, we also curated it with sort of other examples that we found through web scraping, just to sort of like diversify the data. Okay, so once the data has been shaped to how we want it, we run the preprocessing.py script, which it contains the load audio function, which and ensures that the stereo shape is CT, and then resamples to a consistent sampling rate for the entire pipeline, and this ensures uniformity across all the tracks. Then we also have this function, which computes the short time Fourier transform, outputs the magnitude spectrogram and the phase, and then it uses a Hahn window placed on the correct device. And then we have other helper functions like normalize the spectrogram, just normalizes the spectrogram to a zero mean, stabilizes the training and sort of like stops the gradients from blowing up. And then we have compute ratio masks, and they sort of tell the unit like what portion of the mixture belongs to vocal versus like what portion belongs to the instrument. And then we have apply augmentation, which is optional pitch shifting and frequency masking, helps the model organize different types of recordings. File. This is the start of our pipeline. Consistent spectrograms and ratio masks are very important because they enable effective mask learning by the unit. So the next step is going to be dataset.py. Turn to the folders into PyTorch tensors. It also splits the data. So we have 70% training data, 15% validation, and 15% testing. So it ensures that there's fair evaluation and prevents data leakage. It also loads pre-computed spectrogram files, and those are produced during the pre-processing. So why is this important? So the dataset ensures that every training example has the normalized input spectrogram, ground truth vocal mask, and a ground truth instrumental mask, and the mixtures phase. So this dataset module that connects the pre-processing to the model training. Next, we're going to look at the sort of the unit architecture. So this is the architecture that performs the separation. So the key components that we need to talk about is the match size. Match size, which ensures that feature maps aligns during upsampling, and it's critical for skip connection as well. We also need to talk about the convolution block. We're only using 2 convolution blocks based on on our experience trying to tune the model architecture, this is the thing that worked the best. And the convolution block, it captures the local spectral patterns in the time frequency space. Um, so sort of like the unit encoder decoder structure is the encoder is going to downsample the spectrogram and learns the global context. The bottleneck captures the complex instrument and vocal interactions, and the decoder will upsample and recombine with the encoder features and will produce a detailed boundary. And then we have an output layer. And then for an activation, we're using a sigmoid that will constrain a mask from 0 to 1. So then why does this matter? Because the unit is ideal for source separation because it preserves fine details while also still capturing the global structure, and which we think is essential for pulling vocals out of a densely like packed audio file with a lot of instrumentals. Next, we'll be looking at our training file. This is the file that actually trains the model, and we want to highlight the data classes, which has the learning rate hyperparameter, has our optimizer options, early stopping, grading, clipping, and then we also want to look at our data loaders, which we use them for training and validation, and we use the batch size of 1. We also want to look at the optimizer and scheduler. We use AtomW and automatically lowers the learning rate when the validation loss starts to plateau. And then train 1 epoch, which runs the forward pass, computes the L1 loss between the predicted mask and the ground truth, and applies grading, clipping, and updates the weight. And then eval 1 epoch computes validation loss without the gradient updates and ensures the model is generalizing. So this script is the backbone of training. It integrates the dataset, the unit, the loss function, the optimization, and the model. And then finally, we'll look at the scoring pi. Once the model is trained, this script is going to evaluate the audio output. So the metrics that we're sort of measuring from here are the MSE, which is the overall error, MAE, absolute error, and the MEL L1 distance, which is what kind of is our perceptual error. And we also have a signal domain metric, which is the SISDR, which is industry standard separation quality metric. So we want to look at the evaluate pair function, which loads the predicted and the ground truth audio and aligns their lengths and computes the metrics for all of them. Evaluate song runs the inference for one song. So running the inference just means that it runs a song through the model. So it saves the predicted vocal and the instrumental, and it scores both of the stems. And then plot scores just gives us a overall plot of how the model has performed with respect to all the data that has been input. So after running our testing data, we got this plot. To summarize, so the project is meant to be a complete machine learning pipeline for the separation of vocal and instrumentals, and all the components work together to solve the one real problem that we stated at the beginning, which should make it easier for music producers to obtain clean stems for their work for sampling and remixing. And yeah, thank you.
Look how weird this is. Keep watching. What the hell